Okay, perfect. So we are also on YouTube. Let's start. It is a pleasure to have here today Jonathan Stern from Tel Aviv University. Jonathan is a recognized expert on the CGM studies, both from theory, from simulations, and also with comparisons with observations. Jonathan did his PhD on the Technion Israel Institute of Technology in Israel. In 2013, he presented his dissertation. And between 2013 and 2017, he moved to the Max Planck Institute in Heidelberg, also doing these studies of the CGM. Later on, he moved with a Sierra postdoctoral fellow in the Northwestern University from 2017 to 2020. And very, very recently, in 2020, he moved again to Israel, now to the Tel Aviv University, in where he continued with this hard work and very nice work on the CGM studies and trying to figure out how this CGM is formed in external galaxies now that we have better and better observations. Probably I missed a lot of things. Jonathan has a lot of papers on this kind of studies, also organized several seminars, several schools on the CGM and workshops. But well, basically, if you want to mention or one of these or some of these other things that you already, please do it like yourself, and we can start the talk as soon as you want. And thank you for accepting the invitation to give the seminar.
Yeah, thank you, Santi, for the invitation. Yeah, and thank you everybody for joining this virtual seminar. Whoever can turn his camera on, I'd be glad if he does it. It kind of helps to see people's faces when you're talking. Okay, yeah. So should I just share my screen, Santi?
Okay. Yeah. You're gonna start when you want. Yeah.
Okay.
Just a very quick comment also to the audience. If you want to make a question, please before making the question, tell everybody where you're working and your institution, for example, just for other people to know where the question comes from. Thank you.
Okay, and Santi, let me know if somebody raises his hand or if I miss, please let me know. I'd be glad to take questions while I'm talking. Yeah, okay. Okay. Yeah, okay, so yeah, so thanks again, everybody, for joining. I want to talk about the physical processes which drive the formation of galactic disks. Okay, so it's kind of a major question in the physics of galaxy evolution. And kind of the work I'm going to present is based on work I've been doing mainly in my previous position in Northwestern, together with Claude André-Fauché-Giguère and with Drummond Fielding, who's now a postdoc at the CCA, and with Elliot Kruataert, who is now in Princeton. So kind of these three images that you see in the title slide is kind of already gives you the a peek into the main take-home message of this talk. What I'm showing you here are three temperature maps of gas in the galaxy and just around it in a fire cosmological simulation. Okay, and the point I'm going to try to make during this talk is that there's a process in the circumgalactic medium. Okay, so the gas just around the galaxy, which is called virialization. And when the circumgalactic medium virializes, that essentially causes the disks to form. Okay, it actually promotes the formation of disks. Okay, so here you can see kind of that the gas around the galaxy is unvirialized, which means that there's lots of, it's very messy, cold, and hot clumps, and there's no clear disk in the center. And then when the gas virializes, you can see that everything is kind of hot and much more smooth. And in the center, there's a nice central rotating thin disk. Okay, so it's kind of this process of CGM virialization what I want to discuss and what are its implications for the formation of galactic disks. Yeah, and please interrupt me with questions. I would much rather this to be a discussion than just me giving a talk. Okay, so let me just give you some background. what's the first kind of thing I want to discuss is what do observations tell us about where and when galaxies form rotating disks? Okay, so you can see this here. This is a plot of the number density function of galaxies as a function of their stellar mass, and it has this kind of well-known shape, Redshift shape, where it's relatively flat at low stellar masses and then drops above a stellar mass of a few times 10 to the 10, exponentially. And these images show you what are the most common type of galaxy at each stellar mass bit. Okay, so we know that kind of at the massive end of the stellar population, most galaxies are these red and dead ellipticals. Okay, so galaxies which are not star forming and have these ellipsoidal shapes. At intermediate stellar masses, galaxies form these beautiful rotating thin disks. And at the lowest stellar masses, galaxies are still star forming. Okay, they're still blue and star forming, but they have this irregular shape. Okay, it's kind of a disordered shape. It's not a nice disk as you see at higher masses at the lower masses. Okay, so it seems that the rotating galaxies, rotating disks, kind of dominate only at intermediate stellar masses. And this is the rotational velocity of the galaxy, V rot, which is measured from the emission lines of H alpha emission lines, so ionized gas, as a function of the stellar mass of the galaxy. And what I really like about this plot is that instead of using a marker for each type of galaxy, they actually put a small HST image for each galaxy. Okay, so this kind of combination allows them to both show the morphology and the kinematics of the gas in the same plot. Okay, what you can see here is that at high stellar masses, okay, the galaxies fall on a relatively tight relation between rotational velocity and stellar mass, which is known as the Tully-Fisher relation. Okay, it's known since the 70s. But when you go to lower masses, okay, galaxies tend to fall below the extrapolation of the Tully-Fisher relation to lower masses. Okay, so these galaxies both have kind of an irregular shape and a rotational velocity which is below what you expect based on the Tully-Fisher relation of higher mass galaxies. Okay, so this kind of plot shows you that low mass stellar mass are irregular shaped and not dominated by rotation. Their kinematics are not dominated by rotation. And when you go above a mass of something like a few times 10 to the 9, suddenly the blue galaxies are all rotating disks on the Tully-Fisher relation. Okay, so that's the trend with mass, but there's also a trend with redshift. Okay, this has been kind of highlighted a lot in the last decade or so with HST, observations with HST, which show that as you go to higher redshift, the galaxies kind of tend to become clumpier, much more messier, much more irregular, in contrast with kind of the nicer disks that we see in lower redshifts. Okay, so observations in the last decade have kind of shown us very clearly that rotating disks preferably form at high masses and at low redshifts. Okay, while at high redshifts and low masses, galaxies have a more kind of irregular shape and their kinematics are much more disordered. Sorry. Okay. Yeah. Okay, so that's kind of the observations. And now, kind of before describing my own work, I want to kind of give you a brief overview of the general framework for the formation of these galaxies in the context of lambda CDM. So in lambda CDM, okay, the basic picture is that you start with primordial fluctuations in the matter density field, okay, which is dominated by dark matter, and then, as time goes by, due to gravity, these fluctuations tend to grow until they collapse into this network of filaments and nodes known as the cosmic web. Now, the size of these nodes, which are also known as dark matter halos, okay, is set by virial arguments. And the reason is just because the dark matter is dissipationless, Okay, so the size of each node depends on its mass and redshift, and according to virial arguments, you get some size which we mark as the virial radius. Okay. But the gas associated with the dark matter can lose energy by radiatively cooling. Okay, in contrast with the dissipationless dark matter, the gas can lose energy by cooling, and therefore it can further collapse inward towards the center of the dark matter halo. Okay. Now, the basic assumption we make is that as the gas is collapsing and losing energy to radiation, it's conserving angular momentum. Okay, so the collapse of the gas essentially proceeds, okay, until the radius where angular momentum provides support and halts any further collapse. Okay, and it's at that radius where you expect a disk to form and the galaxy and the stars to form. Okay, so okay, so that's kind of the general framework, and then you can calculate what is the expected spin parameter, which is just a measure of the angular momentum that you expect for the gas. So if for a Milky Way halo we expect a virial radius of something like 300 kiloparsec, okay, we expect the angular momentum radius, okay, the radius where the gas can be supported by angular momentum, to be lambda spin times r vir. We know lambda spin from the dark matter simulations, and that gives something like 10 kiloparsec, and that's roughly the size of the Milky Way. Okay, so this kind of basic frameworks correctly predicts the size of the Milky Way and other galaxies. So the question is, okay, so that's a general question. That's a general framework, but the question is this framework sufficient to explain why star-forming disks form preferably at high masses and low redshift? Okay. And the answer is probably no. Okay, the reason is because this halo spin parameter is actually independent of mass and redshift. Okay, so this is a prediction from the Bolshoi-Planck dark matter only simulation. And what's shown here is what is the spin parameter of the halo as a function of halo mass and redshift. And you can see it's pretty constant. Okay, the whole range is mainly a factor of 2. Okay, it's always centered around this value of something like 0.035. Okay, so this is in contrast with kind of the strong trends that we saw in disk galaxies, that disks kind of form preferentially at high mass and low redshift. Okay, so that means that something other than angular momentum conservation is required to explain trends in mass and redshift. And the question is, of course, what is that mechanism? Okay. Okay, so kind of the process I was the system, okay, I want to focus on in this talk is the circumgalactic medium. Okay, so the gas in dark matter halos. And I'm going to suggest that maybe it's the physics of the circumgalactic medium which drive these trends in the kinematics and morphologies that we see in star-forming galaxies. So very, very generally, the circumgalactic medium is defined as gas which is outside the galactic disk, but inside, but still associated with the halo. Okay, so something like the gas between very strong any accretion.
Jonathan, I think we lost you for a couple of minutes, but you are again back online.
Okay. Was that on my end or your end? I'm trying to.
I am not sure.
Okay. Can you see the slides?
Yeah. No. Yes. Yep.
Okay. Yeah. Okay. So where did you lose me? Before the slide or during the slide?
During the slide, in the middle, when you were explaining about the CGM, what is the CGM around the galaxies?
Okay. Okay. So we expect kind of the circumgalactic medium. Okay, the physics of the circum. Wait, am I? Sorry, I'm on the right camera. What's this? Let me. Okay. Okay, are we good now?
Yep.
Okay, great. Okay, so the point I was trying to make is that kind of the physics of the circumgalactic medium are expected to have a very strong effect on the star-forming galaxy, just because any accretion onto the galaxy happens from the circumgalactic medium, and of course, any outflows from the galaxy, their first destination is the circumgalactic medium. Okay, so the question is, can CGM physics explain the kinematic and morphological trends that we see in star-forming galaxies? Okay. Okay, so that was kind of the background, okay, both for the observations and the theory. Now I want to focus on my work. So basically, our approach was to try to model the CGM, okay, that's short for circumgalactic medium, try to model it in a step-by-step approach, an incremental approach, where we start with a very simplistic idealized setup or equations, and then in each step we kind of increase the realism and the complexity of the solution of the equations that we're solving. Okay, so I'm going to start with solving simply one-dimensional steady-state solutions for the circumgalactic medium, and then I'm going to somewhat increase the complexity by showing results from idealized 3D hydrodynamic simulations, and then kind of the last step, we're just showing the results on fully cosmological simulations. Okay, so start simple, try to gain some insights onto the CGM physics, and then test this insight against more and more realistic calculations. Yeah, something stuck. 1 second. Yeah, okay, sorry. Okay, sorry, yeah. Okay, so let's start with steady state solutions for the circumgalactic medium. Okay, so these are the equations that we're solving. It's the conservation of mass, conservation of momentum, and conservation of enthalpy. Okay, it's more convenient to work with enthalpy than with energy in the CGM. So basically, I'll quickly go over the terms. So the equation of mass just tells you that in steady state, okay, so sorry, these equations are the hydrodynamic equations, assuming both steady state and spherical symmetry. Okay, so we drop all the d to d t terms, the d to d phi terms, and the d to d theta terms, and remain only with the d to d r terms. Okay, so once you make these assumptions, the first thing that you get is that the mass inflow rate is a constant. It's constant at different radii, and the mass inflow rate is proportional to r squared times the gas density times the gas velocity. Okay. The momentum equation. Okay, there's a kinetic term. Okay, and then there's a thermal pressure term. Then there's the gravity term. Okay, so this is assumed to be set by the dark matter halo. Okay, so it's a background dark matter halo which dominates the gravity, and that's the consideration. And the fourth term is a centrifugal term. Okay, so we're assuming that the gas has some some rotation, some angular momentum, and therefore it experiences a centrifugal force. Okay, and we parameterize this term using this circularization radius. Okay, this radius where angular momentum can provide support against gravity. And the last equation is just the entropy. Okay, so the change in entropy equals 1 over the radial velocity times the cooling time. Okay, so this term essentially tells that the entropy is determined by the rate of cooling. Cooling time is just the specific energy divided by the specific luminosity of the gas. So this ratio gives you has units of time, and that determines how quickly the gas loses entropy. Okay, so these are equations, and this is a solution for a 10 to the 13 mass halo at redshift 0. This is temperature as a function of radius, and the inflow Mach number as a function of radius. And if you look at the temperature, you see that you get a solution where the gas is relatively hot, above 10 to the 6, temperature comparable to the virial temperature, all through the halo, down to the radius where the gas becomes supported by angular momentum. Okay, so it kind of remains hot, just maybe up to a factor of 1.5 from the angular momentum radius, where it just cools out. That's the temperature. The Mach number in this solution is very, very subsonic. Okay, the inflow is very subsonic. The Mach number is much lower below unity. Okay, that kind of tells you that the solution is very close to hydrostatic, because deviations from hydrostatic go as Mach squared. So if the Mach number is 0.1, that's very close to hydrostatic. And you can see that the Mach number kind of tends to increase as you go inwards. Okay. Now, what you get in these solutions is that the Mach number just equals to the ratio of the cooling time to the free fall time. Okay, the free fall time is something close to the dynamical time of the system. Okay, so in kind of these relatively massive halos of 10 to the 13, the cooling time, the free fall time is something like 10. So you get a relatively low Mach number. Now, these solutions are essentially just cooling flow solutions, which were developed in the late 70s and early 80s for the intercluster medium. And essentially what we did here is just adapt these solutions from the masses of galaxy clusters to the masses of individual galaxies, the halos of individual galaxies. Okay, so this is 10 to the 13. But now I want to show you what happens when I gradually decrease the halo mass. Okay, so first I'll decrease the halo mass a bit. And you can notice that the temperature decreased a little bit, and the cooling time to the Mach number tended to increase a bit. Okay, and I can, yeah, okay. So I'm going to decrease the halo mass, and notice that the Mach number is increasing. Okay, and I'm going to keep decreasing, and the Mach number goes and increases. Okay, the reason the Mach number is increasing while I'm decreasing the halo mass is because the cooling time, the ratio of the cooling time and free fall time is decreasing as you go to lower halo masses. Okay. Now I'm going to approach when I approach a halo mass of 10 to the 12. Okay, you can notice that in the inner regions, just beyond the galaxy, the Mach number becomes very close to unity. Okay, or the ratio of the cooling time and free fall time is roughly 1. Okay, and if I go below 10 to the 12, suddenly a change happens. Okay, so suddenly the solution goes through a sonic point, okay, before hitting before reaching the angular momentum radius. Okay, so notice here how the flow reaches the angular momentum radius subsonically, remains with the Mach number below unity, and kind of slows down before reaching the disk. But once I go through a threshold, suddenly there's a sonic point, and the flow just crashes supersonically into the disk. Okay, so there's a transition that happens in these solutions around the halo mass of 10 to the 12. Okay, so you go from a kind of a cooling flow, a flow which is dominated by cooling, to simply the gas becoming cooling out and free falling and crashing into the disk. If I continue to decrease the halo mass, the sonic point tends to move outwards. Okay, until at some point the sonic point actually goes all the way outwards, and the entire solution is a free fall solution. Okay, it's pure free fall solution at low halo mass. Okay, so what kind of these steady state solutions are telling us is that there are 3 regimes for the circumgalactic medium. Okay, at high halo masses, we have a cooling time larger than free fall time everywhere, so the cooling is relatively low, and we get this cooling flow where the gas is roughly hydrostatic, and kind of the gas gently subsonically accretes onto the galaxy. At low halo masses, okay, the gas is supersonic everywhere. Okay, so the cooling time is short everywhere, and the gas is just free falling all the way from the IGM, crashing into the galaxy. And what's kind of new from our results compared to previous results by White and Rees and Deckel is that there's also an intermediate regime, okay, where the gas is slowly cooling, so quasi-hydrostatic in the outer halo, but the cooling is rapid in the inner halo, so the gas kind of goes through a sonic point from kind of gentle accretion to free fall. Okay, and what I want you to notice is that this transition, okay, is a transition where where the properties of galaxy accretion change. Okay, so in both these cases, accretion onto the gas is crashing supersonically, and here it's more like gentle subsonic accretion. Okay, so this is where we expect a big change in the properties of inflow and maybe the properties of the galaxy. Okay, and this change happens when the cooling time roughly equals the fluid flow time at something like 10% of the virial radius. Okay, so that's that's in the steady state solutions. Okay, in the next step, we actually use Idealize 3D CGM simulations. And these simulations were set up and run by Drummond Fielding, okay, using the Athena++ code. So he definitely deserves most of the credit. The setup is relatively simple. We want to focus on the CGM. So we assume that the background dark matter halo is constant, just sets the gravitational field. We treat the IGM as an outer boundary. We treat star formation just as a gas sink in the center of the simulation. And we initially fill the CGM with gas, which is hydrostatic and slightly rotating. Okay. And what you can see here on the right is 3 snapshots from these simulations, okay, where the simulation essentially converged onto one of the regimes that we saw before for the steady state solution. Okay, so we have here a kind of snapshot, which is an edge-on view. Okay, so the galaxy disk is over here. Okay, color is temperature, and the lines are just the flow lines. So this is kind of the fully subsonic solution. You can see that there's a kind of weak inflow which converges onto the angular momentum radius. Here is this transonic solution where you have gas in the outer part, which is hot and subsonic, going through a sonic point and then crashing into the disk. And these are kind of these full supersonic solutions. Okay. So kind of the conclusion from these 3D hydrodynamic simulations is that even when you consider kind of perturbations and time dependencies and deviations from circular symmetry, you still get something that resembles the 3 steady state solutions that we found in the beginning. Okay. Okay, so yeah. So the next step is the fire cosmological simulations. Okay. So this is kind of the most realistic calculations which are now being done. Basically, you start with cosmological initial conditions. These are fire zoom simulations, so similar to what Santi often runs and analyzes, where you kind of simulate a single main halo and its central galaxy with very high resolution, but in a kind of fully cosmological environment. You start with cosmological initial conditions, and you calculate gravity, hydro, and cooling, and add these subgrid prescriptions for stellar processes which we think affect the evolution of galaxy, specifically star formation and feedback, including supernova, stellar winds, and radiation. Okay, so what I want to show you is a movie of a fire simulation of a Milky Way-like galaxies, a Milky Way-like galaxy. Okay, so it's just that the color here is just the temperature of the gas, with red being hot gas, green being kind of warm gas, and magenta cold gas. Yeah, okay. Okay, so we start with cosmological conditions. This is the initial expansion and the growth of the perturbations. You will see these strong bursts going on. These strong bursts are the strong feedback in the center, in the various galaxies. What I want you to notice is that initially everything is kind of very irregular and kind of chaotic, and there's these strong bursts. But at some point, these things will kind of die off, and you will see a rotating disk form. Okay, now we're after redshift 0.5. Okay, you can see that the bursts are almost gone, and we see these nice rotating disks. Okay, a small satellite comes in. Okay. So that's a simulation. And now the question is, do we see the same types of CGM that we saw in the steady state solutions and the idealized numerical experiments? Do we see them also in these cosmological simulations? And it seems that we do. Okay, so I'm going to show you here two snapshots from two different simulations. The Redshift 0 snapshot. This is for a halo mass of 10 to the 12. And this is a halo mass, a slightly smaller lower mass of 3 times 10 to the 11. Okay, so this is for a Milky Way-like galaxy, and this is for a dwarf galaxy. And what I'm showing here is the temperature map of gas, and you can see that the CGM is filled with hot gas. Okay, gas which is roughly at the virial temperature of the halo. And if you zoom in, you can see that this hot gas extends up to a few disk scale heights above the disk. Okay, so everything is hot down to this nice thin disk where within it the gas is pretty cold. Okay. Now, if we look at the slightly lower mass halo with the dwarf galaxy, you can see that the outer halo is still hot. Okay, it's still kind of most of the volume is filled with gas with a temperature comparable to the virial temperature. So in the outer halo here seems pretty close to what we see here. But the inner halo is very different. Okay, so here we see an inner halo where a large fraction of the volume is filled by cool gas with these occasional kind of clumps of hot gas. So here we see kind of hot gas plus thin disk, and here's kind of everything is messy, much more irregular shape, much more disordered kinematics. Okay, so it seems that kind of these two CGM regimes that we saw in the steady state solutions also materialize in the cosmological simulations. Fully hot CGM above 10 to the 12, and below 10 to the 12, we see these transonic CGM, okay, where we have a hot outer CGM and a cool inner CGM. And we also see that this transition seems to be related to the formation of the disk. Okay. Okay, so previously I showed you two different halos at Redshift 0. Now I'm going to show you the same halo at different times. Okay, so we're going from snapshots from Redshift 1 down to Redshift 0. Okay, and you can see here that the ratio of the cooling time and freefall time at the inner CGM, so at 10% of the race, kind of increases from 0.25 at Redshift 1 all the way to 16 at Redshift 1. And you can see this transition in a given halo between kind of this very messy CGM, lots of cool gas, lots of hot gas, very clumpy, no clear disk, to a fully hot inner CGM with a nice thin disk in the center. Okay, so it seems kind of that as the cooling time exceeds the freefall time in the inner CGM, okay, you essentially form this thin disk. Okay, so we call this process, we call it inner CGM virialization. Okay, this transition between a clumpy, cool CGM to a smooth, hot CGM, the virialization of the inner CGM. Okay, so essentially a transition between this transonic CGM to a hot CGM. This is what it looks like in terms of temperature. The bottom row showed what it looks like in terms of pressure. Okay, so the color here is the pressure divided by the average pressure in a given radial sphere. Okay, so it shows you the pressure, but removing the radial trend in pressure. And you can see that before virialization, the gas is actually out of sonic contact, okay, because everything is supersonic. Okay, so we have these huge pressure fluctuations. Okay, so we see lots of channel of low pressure, and lots of regions with a high pressure. But once the inner CGM virializes, everything becomes kind of uniform, and the disk is essentially confined by a very close to uniform CGM pressure. Okay. So we previously saw that this transition has kind of a very strong effect on how gas accretes onto the galaxy, but the transition in the pressure also suggests that it will have a very big effect on how outflows expand from the galaxy. Okay. So here, if there's an outflow in the central galaxy, it can easily expand through these low pressure channels, these paths of least resistance. While here, if outflows come from the disk, they will kind of hit a wall in the CGM, which has a constant uniform pressure. So this kind of CGM will much more easily confine outflows to remain in the disk. Okay, so this is another way of showing the same thing. Okay, so here I'm looking at gas kinematics. What I'm showing you here is the gas kinematics as a function of radius from the galaxy. The y-axis is the rotational velocity divided by the dispersion. So this gives you a sense of how important rotation is at each radius. And each line here gives you a different time. Okay, so blue lines are early times when the cooling is rapid, and you can see, okay, that essentially the rotation, this ratio is about unity. Okay, that means that the kinematics are entirely disordered. And as time goes by, okay, the cooling time increases. At some point, the inner CGM virializes, and then you get these red lines where the rotational velocity is much higher than the dispersion. Okay, so this would be a thin disk, and this will be an irregular with disordered kinematics. Okay. So what we're finding here is kind of something that has not been appreciated before, and that is that there's a strong relation between the thermal properties of the circumgalactic medium and the kinematics of the central galaxy. Okay, I'm almost done. We see one additional thing that came out of this analysis of the fire simulations is that there's additional transitions which are associated with the visualization of the inner CGM. Okay, so these are transitions which have been known for a while in the fire simulation. Okay, but until now we didn't know what causes them. So one transition is in the star formation rate. Okay, you can see that at higher redshift, the star formation rate is very bursty. Okay, so the blue line is kind of the instantaneous star formation rate, and the black line is kind of running mean. And you see that there's like these strong bursts of star formation rate until a redshift of something like 0.3, and then suddenly the bursts almost decrease. Okay, and everything becomes much more steady. And you see a similar behavior in the mass flow rate at 10% of the virial radius. Okay, you can see these strong bursts of outflows at early times, okay, and then at some point these bursts just disappear, and you get a much steady inflow in the inner CGM. Okay, and this transition is pretty sharp. Okay? And what we show here is actually this transition corresponds to where the cooling time exceeds the free fall time, and the inner CGM virializes. Okay? So this is for one halo. This is a Milky Way-like halo with a halo mass of 10 to 12 redshift 0. But we also did this for other halos. This is another halo. Okay, you can see here again the bursty star formation phase followed by a steady phase. Here the transition happens at a higher redshift of something like 0.7. But again, the transition corresponds to when the inner CGM virializes, when the cooling time exceeds the free fall time. In this halo, which is a much more massive halo, it has a halo of 4 times 10 to the 12 already at redshift 1. Okay, so this would be a group sizes halo at redshift 0. You see the same behavior, bursty star formation at high redshift, followed by steady star formation at low redshift. Same for the outflows. The transition happens at a much higher redshift of 3.5, and it still coincides with where the cooling time exceeds the free fall time. Okay, so still it coincides with where the inner CGM virializes. Okay? So this analysis is kind of suggesting that these kind of transitions that we saw in the fire simulations that we know about may be driven by the thermal properties of the circumgalactic medium. Okay, so one last slide before I summarize is a cartoon picture of what we think is going on. Okay, and this is something we are working now with several students are now working on kind of understanding the details of this picture. So basically, we assume that at low masses high z, okay, before the inner CGM has virialized, okay, we have these kind of clumps which are free falling onto the galaxy. Okay, so these clumps are just free falling, crashing on the galaxies, and then they have these bursts of star formation, and then these outflows can just freely expand through the low pressure channels. Okay, so kind of in this violet regime that we have at low masses, the galaxy just repeatedly blows itself apart in these cycles of inflows, star formation, and outflows. Once we cross the threshold, the inner CGM virializes, and now we have this nice disk with an inner CGM, kind of a virialized inner CGM confining it. The accretion becomes smooth and subsonic, so very gentle, and the winds are confined by the uniform CGM pressure. Okay, and once this happens, then we get a stable disk with a steady state star formation. Okay, so kind of the standard model for the for a galaxy disk, where everything is kind of in vertical pressure equilibrium and star formation rate is steady, only applies after the inner CGM forms. Okay, before we have this kind of violent, irregular, disordered kinematics. Okay, and that's basically it. Okay, two take-home messages. One is that there's three regimes for the CGM. Okay, so previous studies have typically assumed that the CGM can be entirely cold, entirely hot. We're showing that there's another regime where the CGM is hot in the outer part and cold in the inner part, what we call a transonic CGM. And that the transition from transonic to hot, it drives the formation of this formation. Okay, so the transition between irregular galaxies and disk galaxies happens when the CGM goes from being transonic to hot all the way down to the galaxy. And yeah, and that's about it.
Great. Thank you, Jonathan, for a very nice talk and very illustrative and very clear. I have several questions, but I first want to ask to the audience if somebody has a question, they can proceed first and I will be the one later. So if the audience has any question to Jonathan, please just raise your hand or you can unmute yourself. If not, well, you can do it later. I can start with the questions then. Jonathan, first of all, one thing that is probably a little bit more technical and probably is you are not the one to ask, but the people that run FIRE. Well, it's two technical questions, but you probably already answered these questions several other times. The first one is the FIRE simulations is basically SPH. We know that SPH doesn't trace very well the low density regions. So have you tried to analyze this in an AMR code based simulation?
Not yet. So we want to look at this in other simulations as well, mainly kind of the public version of Elasticity and G50 and other simulations. We do see this, what we do have, so that's kind of for the cosmological simulations. We do, though, the Idealize simulations that I showed that are grid simulations. Okay, these Athena simulations are grid, and kind of we see the same processes happening. Okay, so we think at least that it's not, it's not something specific for the hydrodynamic code. Okay, good, perfect. And the other thing is that also we know that FIRE usually has a stronger feedback than other models. Do you expect any change like a global change, or maybe having a stronger or weaker feedback will just delay a bit or change a bit the moment of the transition between the subsonic and the supersonic regimes? Yeah, okay, so there's kind of two separate effects for feedback here, okay? So one, kind of the simple effect of feedback is that it changes the CGM metallicity, and it can also, by evacuating the CGM, change its density, okay? And then this density and metallicity affect the cooling time, okay? So according to how, so if you have strong feedback, you tend to enrich the CGM more, but you tend to evacuate it more, and that depending on what changes, that will change the cooling time, and then kind of when this process happens. So that's one effect. Of course, the other effect is the dynamical effect of feedback, right? That you're heating the gas very quickly. Okay, so you're injecting a lot of heat, and that kind of what feedback could change this picture. Okay, specifically in FIRE, you're injecting very strong winds, but they don't have a high specific energy. Okay, so the velocity of the winds is close to the circular velocity of the galaxy or to the escape velocity. It's not like a factor of 10 above the escape velocity. It's not much higher. Okay, so the cooling times of shocked winds is very similar to the cooling time of accreted gas. Okay, and therefore, if you inject gas which has velocities comparable to escape velocities, nothing will change. So you have essentially the same picture here. you can think about kind of feedback which injects very high specific energy particles, maybe like AGN jet feedback. Okay, that could actually change what's going on. Okay, these simulations in fire don't have AGN feedback. Hopefully, AGN feedback in reality doesn't matter a lot because these irregulars have kind of very small black holes. Okay, so I think it's reasonable in the irregular phase to kind of neglect black hole feedback. So at least until the transition, I think it's reasonable to neglect black hole feedback. After the disk forms and kind of the process that I'm discussing happens, then maybe the black hole starts to grow, and then it can change it will likely change the rest of the evolution of the CGM. But I think for this transition, neglecting AGN feedback is a reasonable assumption.
Good. And I have a question regarding the redshift dependence, because basically you are applying a model and comparing this model with simulations, and also probably the simplified models you use at first to somehow the scenario we have at low redshift. But we have this increase on metals, that increasing metals means that you are lowering down the cooling time. So you are also changing, with increasing the metals in the CGM, you are also changing the cooling times. So do you expect, or you have checked if there is a redshift dependence also in this scenario? At high redshift, the things probably work different because the metals are lower, or?
Yes. Yeah. So yeah, exactly. So that's, I think, what I really think kind of creates the redshift dependence is the change of the metallicity, like you say, but also the change in density. So based on like X-ray observations, X-ray emission from the CGM, okay, it seems reasonable that in local galaxies, a large fraction of CGM has been lost. Okay, so outflows at high redshift have kind of evacuated some part of the CGM. So it seems that the CGM density relative to kind of the halo baryon budget decreases with a decreasing redshift. Okay, so decreases with time, and that would cause the threshold for virialization to be lower at a low redshift. Okay, so at high redshift, we set let's say the threshold to be something like 10 to the 12, and at low redshift, maybe something closer to 10 to the 11, due to this effect of the gas evacuating, the CGM being evacuated by outflows at higher redshift, evacuated, lower density, and longer cooling times.
Mm-hmm. And a very last one from my side is the dependence on the environment. Probably a very isolated galaxy at the lower redshift is quite different from a one that has a lot of interactions at low redshift, basically because you are perturbing and maybe also somehow helping the galaxy to virialize the CGM if it is richer in mergers. I don't know if you check it, if there is this dependence on the environment in models and simulations. You expect to do it in the future?
So I don't think I fully followed your question. So you're saying, how do mergers affect this picture? Is that the question?
The dependence on the merger scenario, because for example, you said that at low redshift, you can see that the star formation history of the main galaxy, of the central galaxy, is much softer. But well, this is much softer maybe because you are not having a lots of interactions. You are in a kind of isolated region. But for example, a Milky Way-like galaxy in a cluster, you are still having a lot of interactions at low redshift. Then maybe the picture is different.
Yeah, I see. So this picture definitely neglects mergers. Okay, it assumes, so the idealized models don't have mergers at all. Okay, and kind of, I think what we're finding kind of this relation, let me go back for a second. Right. So the fact kind of that this bursty phase ends exactly when the CGM virializes kind of suggests it's not mergers which are changing this. The end of this bursty phase doesn't seem to be driven by the end of mergers. Okay,
but you check it when the last merger occurred, because maybe the last merger is the one that triggered the virialization, and then you don't know what is the cause and what is the consequence.
No, the virialization cannot be triggered by mergers, because the virialization is just kind of these basic gas physics. Okay, What can happen is that if you have a merger, and we see this in some simulations, if you have a merger after the virialization, then suddenly you see kind of another bursty phase, like a short burst of star formation following a merger. Okay, that we definitely see. But this is not, right, what's happening here is not mergers. Every dynamical time, like before virialization, every dynamical time, the galaxy is blowing itself apart and then kind of inflow, star formation, outflow. Every dynamical time. Yeah. So it's not some external process that's happening. And actually, you can see this process even in isolated galaxies. Like David de Martise has a simulation where he shows the galaxies continually, the feedback is blowing itself apart, and then kind of reaccreting, and the cycle repeats itself. So this seems to end when the CGM virializes. Okay, and then if you have a merger, then you could have another burst kind of at a later time. Okay, that's the idea. And it seems, from what we looked at, because we're looking at mergers in these simulations, it seems consistent. I'll tell you more of this, right? Like, look here, right here, the bursty phase ends in these kind of Milky Way mass halos. The bursty phase ends at redshift 0.3, and in these massive halos, the bursty phase ends at redshift 3.5. Okay, so you would expect in these halos mergers. I don't expect. I know that in these halos mergers continue even after the bursty phase. Okay, they just don't have such a huge effect.
Okay, and the difference between the first and the second column is basically the assembling history. The second one reaches the 1 times 10 to the 12, the 5 times 10 to the 11 before the other one. It's just assembling history, the difference here.
Yes, essentially, yes. The thing is, there's also the angular momentum is slightly different between the two halos, and that also matters because it changes a bit the behavior of when the CGM virializes. So there are small differences. Small differences in the initial conditions of the two halos can make a big difference in terms of when the CGM virializes.
Interesting. Good. Well, just to finish, to tell you that you are extremely welcome to start with the Agora 6 different models of a Milky Way-like galaxy with 6 different codes. It will be very good if you can do this analysis there with these models. We can talk about that. I will send you an email about that.
Yes, let's definitely do that. Yes, that sounds great. Yeah.
Perfect. Good. So if anybody else has a question in the audience. Okay, so if nobody else wants to ask a question, we can just leave it here. It keeps recorded in YouTube, so probably if we have a question through email, it happened in the past. We will tell the people to contact you directly for questions on your work. Okay. Thank you a lot for the seminar. It was very interesting to talk. And see you soon, I hope.
Thank you, Santi. Thank you. Thank you, everybody.
Thank you, Jonathan. And to the audience, the next week we have another talk on Wednesday. Let me check just who the speaker is. We have Antonio Hales that will talk about recent observations, highlighted the concept of disk settling. Yeah. So you are welcome to come to the next seminar next Wednesday, same time. Thank you a lot, Jonathan, and see you soon.
Yeah.
Thanks. Bye.